Hey everybody, and welcome to the stream, or in this case the recordings, since this one's going for YouTube and it's a little bit different than the one that we did on the live stream, mostly because there was an error in one of the examples, and so I wanted to redo that to not confuse people that are not watching it live. So there we go. All right, so let's go ahead and get started then. Okay, so here we go. This is week 13, day 2, and today we're going to be talking about minimum spanning trees. Specifically, we're going to be talking about Prim's minimum spanning tree algorithm after I give you a brief introduction into what a minimum spanning tree is. After that, next class, I just wanted to tell you that we will be talking about disjoint sets, which are used in the other algorithm that you will learn for minimum spanning trees, which is Kruskal's minimum spanning tree algorithm. So you can see they got different time complexities. So you definitely do not want to do the v squared version, but that's the one that I'm going to show you. The difference being that the e log b version is when you're using a binary heap, and that's going to be the fastest one. On the other hand, Kruskal's, you got e log b and e log e added together. But remember, if you're adding n plus n, which becomes 2n, that's just really n if you're thinking of big O and that sort of thing. So really, you could say that they are comparable in a way, but theoretically, Kruskal's is a tiny little bit slower in that regards. So what is a minimum spanning tree? A minimum spanning tree is going to be a form of a graph. I know the word tree is a little bit misleading, but it's typically considered a graph. In fact, any tree is a graph, actually. But it's a subgraph that connects as many vertices as the original graph that you were given, but it keeps the sum of the edge weights, so we're talking about a weighted graph, to a minimum. And because of this, it is possible that there may or may not be more than one minimum spanning tree per a given graph. Okay? The other definition, here's one from Wikipedia, which might be useful to read, maybe makes more sense to you, is a minimum weight spanning tree is a subset of edges of a connected edge-weighted undirected graph that connects all the vertices together without any cycles. That is important, and it's going to come into play when we talk about Kruskal's, and with the minimum possible total edge weight. That is, a spanning tree whose sum of the edge weights is as small as possible. More generally, any edge-weighted undirected graph, not necessarily connected, has a minimum spanning forest, which is a union of the minimum spanning tree and its connected components. So, what does that actually look like when it's not just a bunch of words put together? Okay, so I want you to take a look at the graph that we have on the top left. So this graph, that's the one that I want you to consider, okay? This graph has 4 vertices and it has 5 edges, right? We could list them out as saying A to B with a weight of 2 and A to D with a weight of 2. So if I was to ask you, and you can think of this as a computer network and the internet. And if I was to ask you, if I want to send a piece of communication information from A and I want to send it to C, how many different paths could this communication take? And so one of the most direct ways of sending it would be to go A to B and B to C. And if I was to tell you that that weight is actually time the signal takes to travel to, say, this network, then you would tell me that it takes 5 seconds, assuming that there's no time in repeating the signal in B to get to C. What other routes could you take? Well, you could go down this way to D, and then from D you could go to C. Now this is a slower route because it's going to take 7 seconds, because even though the hop from A to D is the same time from the A to B, the second hop is going to be a little bit longer, right? Are there any other paths that you could take? Of course, there's actually an infinite amount if you repeat vertices. Because you could also do, well, you could do this one too, first of all. So let me show you one more that's very different. And that is if you take A to B, B to D, and then D to C. Now that's a long path. It's actually the slowest one so far that I've shown you, because that's going to take actually a total of 8 seconds to go, right? But I could also do something weird in a way, and clean that up, where I go like this to B, and then maybe actually from B, so A to B, B to D, D back to A back to B a second time, B back to D a second time, then back to A, and then maybe back to B, and then finally to C. Now that's very, very inefficient and somewhat pointless. You wouldn't want to do that, but theoretically, that shows you that there's more than one sort of way of getting there. So, if I was to tell you a different question now, suppose that we wanted to get to D, okay? If I want to go from A to D, I could go this direction, but I could also go this direction. Now this is a direct connection, right? This is a direct connection, and you might be like, well, a direct connection is better. Well, we're assuming that there's no added delay when the signal is being repeated. However, even in that case, the direct connection is faster because this takes 2 seconds versus that one taking 2 and 1 second, okay? Fair enough. One more example. Suppose that I told you that I wanted you to go from suppose I wanted you to go from, what's a good example here? I had one in my head and they just went away. Here we go. I remember now. I want to go from D to C, okay? Or C to D, doesn't matter. In this case, the direct connection is actually slower than the connection that goes through a different place. So the one that goes to B first and then to C, that connection is actually faster than the direct connection. So this is like saying my internet is slower, even though I got a direct connection to the server, is slower than me connecting to my neighbor's internet and then using his. Why? Because maybe my connection is some DSL and he has fiber. And so my DSL connection to my neighbor takes 1 second, but my DSL connection to the main central takes 5 seconds. But if I connect to my neighbor in 1 second, and then he relays the signal to the server with his fiber network, it's actually going to take him 3 seconds. And so it's actually 1 second faster to use my neighbor as a relay than it is to send the connection directly myself because I have such a slow connection. So it's not always the case that a direct connection or an actual edge that exists between you and your destination is the fastest way to get there. Okay? But I don't want you to confuse minimum spanning trees with shortest path, which is like Dijkstra's shortest path or other shortest path algorithms. Because minimum spanning trees are a more relaxed version of a shortest path problem. A shortest path problem typically says, I want to go from point A to point B the fastest way. It doesn't matter if I take some relay route where I have to go and visit other people in the process, or if I take the straight run. You know, if this is saying, you know, this is like taking the 215 highway versus taking the roads. The roads is a direct path, but it's actually slower than the highway, which is a bigger path because you're kind of going around the city. If you live in like Vegas 215, which is a periphery highway. So because of that, ultimately, we are looking at more than just the time, but we're also trying to look at the efficiency. So if you're trying to come up with a network for a house, or sorry, not just for a house, but for a community that you're building of new houses, and I told you, you know, budget cuts. We're trying to have everybody connected to the internet with the least amount of cable possible or wiring possible. And I told you that instead of the reason why these are 2 and 3 seconds and 1 second is no longer because it's a DSL or because it's fiber, but now we're talking distance. We're saying that the line from C to D that takes 5, that's a 5 kilometer cable that we have to lie down so we can connect those 2 houses together. And so if I told you that, let's just pick A and say that A is going to be the central, okay? So that's going to be the central station. And from there, you can communicate to the World Wide Web and so on, okay? So if I tell you that that's the the central where the communication is going to be sent, it means that everybody has to have a connection in one way or another to that node. They have to be able to communicate there, okay? Now, if it doesn't matter how long it takes them to communicate, as long as they have a path to that node, they should have access to the internet, whether it's slow or not. So is that the case here? Yeah, he can go this way, or he can even go this way. He can also go this way, and you can see there's more than one route they can take. That tells me that I can remove one of these lines and still maintain connectivity in my network. So I can go ahead and just remove, for example, this line, and I haven't lost connectivity. Any of my nodes can connect to A, and they can actually communicate to each other. However, for example, if C wants to communicate with A, now it has to go through D. If it's forced to go through D. In fact, it's the only way then they can go. Okay? I could even remove one more of these and still get away with it, but not any of them. I cannot remove this one because then I lose C. C becomes isolated from the internet. I can, however, maybe remove this one. And now every single node is connected to A. They have a path to A. It's not necessarily the most efficient way, you know. Before we had a line here that was 2, right? And so if D wanted to connect to the internet, it took him 2 seconds, you know, for 2 kilometers of cable. But now it's taking him 3 kilometers and he has to go through B. And so this is, you know, budget savings, you know. You still maintain connectivity even though you lose speed per se or time. So if the idea is to try and reduce the amount of extra unnecessary, in the sense if you don't care about speed, wiring, which lines do you actually remove? Do you just remove the ones that I picked randomly? And the answer is no. You don't want to pick randomly. You want to remove the heaviest lines, so the ones that are the longest, but that do not break the connectivity. So in this case, actually the one that I really want to get rid of is the biggest one, which is this 5. I want to get rid of this 5 because that's 5 kilometers of cable I'm saving. If I want to add, the original network is 5 plus 2 plus 2 plus 3 plus 1. That's a total of 13. 13 kilometers of wiring for 4 houses, basically. And here's the thing. If I go ahead and get rid of this guy, I'm saving 5 kilometers of wiring, and now I'm down to potentially 8 kilometers of wiring. Furthermore, I can remove one more of these edges and still get away with connectivity. Now I gotta be careful. I cannot remove this one anymore, even though it's the heaviest one and it's the one that I wish I could remove. I cannot, because then C is stuck out of the loop and now it has no internet. So really, I'm limited to removing this one, or this one. And of course, I'm trying to save the most money possible, so I'm going to remove the longest one here. So either of the 2 kilometer ones. Either one is fine. So in this case, I'm going to go ahead and just pick to remove that one arbitrarily. But either one would be okay. Okay. In fact, actually, you know, I don't like lines crossing, but so I'm actually going to remove this one just to avoid that line cross because it looks prettier that way. Yeah, why not? Line crossing doesn't matter. It's just personal. Like, it just looks prettier. I could have redrawn this in a way to avoid crossings, actually, if I wanted to keep that edge by having that edge be out here like that. That would have been worked as well, too. That has to do with the whole Hamiltonian path and Euler bridges and all that stuff. Anyways, this is now going to be a minimum spanning tree. It's a graph that maintains the same connectivity you started with, but it has the least amount of edges possible. And it actually turns out that it has V minus 1 edges. So I have that here. And that happens to be always the case. A minimum spanning tree is going to have V, which is the number of vertices, minus 1. And that's the number of edges you have. And it makes sense because if you have 4 nodes or 4 vertices, you need at least 3 lines to connect them all. At least. You may need more, but at the very least you would need them. Don't try to come up with an example that would only require 2 lines, and it's impossible. However, I can come up with tons of examples that would have at least 4 lines, and one of them would be redundant. In fact, there's no way you can add another line here that is critical, because otherwise this wouldn't work. Okay? So that's essentially the basics of how a minimum spanning tree works. And what you see here that I have next to it are that there may be more than one answer. Notice that when we decided to take one of the 2s out, we picked arbitrarily. And so depending on which one we have taken out, we would have ended up with different trees. Here we have one tree we could have ended up with, and we have another one. And they're both actually the minimum spanning trees. I went ahead and created a dotted line to represent a line that's gone. So that's not part of the tree, but I can go ahead and get rid of it. So that's the edge that I removed that was redundant. And as you can see, both of these are perfectly valid minimum spanning trees. Not all graphs have more than one minimum spanning tree. It strictly depends on the weight. So if you think back of what the math says here, is that the sum of the weights is going to be the smallest number. So the minimum spanning tree, if you add up all the weights, the 2, the 3, the 1, and the 5, notice that in my minimum spanning tree, I have a total weight of 6. Okay, so all my minimum spanning trees are guaranteed to have a weight of 6. There's no minimum spanning tree that can have more or less. Otherwise, if there was something less, then that would be the real minimum spanning tree. And if there's something more, then that means that it's not the best case scenario, which means there's a better one out there, which is the one that's left, right? So ultimately, a minimum spanning tree, while there may be multiple, if there's multiple, they will have the same weight. So here's another example of a potential minimum spanning tree, but there's something wrong with it. And that happens to be the case that if I add these together, I'm going to get 3 plus 2 is 5 plus 2 is 7. 7 is more than 6. And because there are 2 cases where I have 6, then that tells me that this cannot be a minimum spanning tree. And it makes sense. Why? Because the way that I have this here, you know, I can't remove any edges because I would have lost connectivity to either C or D here. But, you know, the original graph was this. So I should have not removed this one, you know, and then if I didn't remove this one, then I would be able to remove one of the 2's, and I would have ended up with 6, right? But I went ahead and did that, and so that's why I ended up with this not so efficient version, right? So these are, of course, toy examples, but when you have a big graph, it's not so easy to visualize this, which is why I'm going to show you a systematic way of doing this using those 2 algorithms. Here's 2 more examples. In the one over here, we don't lose connectivity either. And you can see that the added weight is 8 though. That's not as efficient as 6. I need 2 more kilometers to do this system. And so that's why it's not a minimum spanning tree. And finally, the last one, we have a weight of 5. You're thinking, oh, well, that's less than 6. That's a better choice. Yeah, but the catch is that C is now isolated from the network and they have no internet. And so the goal is we want to maintain that connectivity that we started with and go ahead and actually use that as the minimum requirement. If something was connected in that network there, it must remain connected. And that's how you end up with V minus 1, assuming that all the edges were connected and there was some sort of path. All right, so now I have a bigger example here. And before I show you the actual algorithms, at least Prim today, I'm going to show you how to do minimum spanning tree sort of by winging it, by visually winging it. And that can be useful for toy examples and also to better understand how it works. And this is actually going to be kind of similar to Kruskal's algorithm, except sort of kind of backwards because it makes it easier for drawing purposes. So when on Tuesday we come back to that, you will actually see that it's a little bit similar in that regard. So the way this works is we're going to start to jank edges out from the most expensive one to the cheapest one until we cannot do it anymore because we lose connectivity. And so what's the most expensive edge here? 14. That's the biggest one. That's the heavy one. That's 14 kilometers of wiring that we don't need. Because if we remove that, we still have connectivity. Okay? All right. What else can we get rid of? What is the next biggest one? 11. Can we get rid of that? Yes, we can. Because we still have a way of reaching 1 and 7. And as long as there's another alternate way of communicating between those 2 nodes, you do not need it. Think about cycles for a second as a way to refresh that. All right, what about the next one? The next one will be 10. Is there, if we delete this edge here, is there still a way to communicate between 5 and 4? Yes, there is, because you could just go all the way around. And therefore, we can go ahead and get rid of 10. All right, what's this the next biggest number? 9. So now we're looking at this 9. We ask ourselves, if we go ahead and we get rid of this edge, do we still have a way of getting from here to here? The answer is no. We would lose connectivity in that case. Therefore, that's an edge that we have to keep. So we're going to go ahead and let it be because we have no choice. Okay, what's next? 8. Okay, what about, we have two 8s in this case. We have this 8 and we have this 8. So either one of those could go away because if we get rid of this one, we still have a way of communicating between those. And if we, this one away, if we get rid of this one, we still have a way of communicating there as well. So because there are two choices that we can get rid of, that means that this graph has more than one solution for the minimum spanning tree. And so in this case, we are just going to arbitrarily pick to remove this one. And if I do that, then I can continue now. As I see, I would look at the, technically, algorithmically, I'd look at this second 8 and I would try to remove it, but I cannot because I would lose connection between the 1 and the 2 and also the 0. So that has to be part of the minimum spanning tree. All right, let's look at the 7. Can I remove the 7? Here, I cannot, because if I remove this 7, I'm going to lose connectivity between the 3 and the 2, and actually the 4 as well. Okay, could I remove this 7 here? And the answer is yes, because I will still be able to communicate between 8 and 7 via 6. So let's go ahead and get rid of that. Perfect. Okay, next one is the 6. Can I get rid of that? Can I get rid of this without losing connectivity? And the answer is yes, because I can still do that. Awesome. So let's get rid of that one too then. Okay, and it turns out that at this point I'm actually done. I'm done with the with the number of edges that I can get rid of. If I was to keep going, I would see that I cannot remove this 4, and I cannot remove this 4 either here. So neither this one or that one can I remove. And I cannot remove this 2 because I lose the 8. And I cannot remove that because I lose the 6 and the 7. And I can remove that because I lose the 7. So at that point, the remaining edges are going to be part of the minimum spanning tree. And if we were to count them, you know, we got 1, 2, 3, 4, 5, 6, 7, 8. We have 8 edges, and we have actually 9 vertices. And b minus 1 is 8, so that does tell us that we are done as well. Do note, though, that this edge that we got rid of here, which was of size 8, that would also be an alternative and a solution to our minimum spanning tree. Oh, perfect. I have another one up here. So let's go ahead and actually do that over here. So what that would have looked like, and I'll do this one much quicker, is you start out by removing the 14, and then the 11, and then the 9. Oh, sorry, not the 9. Sorry, the 10, because that's a bigger number first. You know, we're greedy in that sense. We're always removing the biggest numbers. We can't remove the 9, but now we're going to remove this 8 instead. So this has to be there. This has to be there. That has to be there for sure. That has to be there for sure. And then we got to remove the next one, which is going to be the biggest one, which is the 7. And then the 6. And then this has to be there. This, and this. And so here you have the same graph generating two completely different minimum spanning trees. If we were to add the weights of all of the edges, you would see that both graphs have the same weight, which is the minimum weight that they can have, the least amount of cable required for this network. If you want to add that, that's basically 4 plus 8, which is 12, plus 9, which is 21, plus 7, which is 28, plus 6 is 34, plus 3 is 37. So I do believe, if I did not make an arithmetic error, that the weight of this graph is 37, meaning that we need 37 kilometers of cable in the cheapest sense. Now, is this good for all the customers here? Of course not. I mean, they're going to be basically overloaded. Like, if the person that in house 7 is watching Netflix and just literally hoarding the internet, the person at 6, or actually, well, either way it could work. Then 6 would suffer, but also if 6 is using it, then 7 would suffer, right? And technically, if 1 is using the internet, he's literally throttling and holding back the entire network because he's the only one that's connected to the central here, technically. And so Minimum spanning trees are, yes, efficient for trying to keep things as least amount of infrastructure as required, as needed, but they're not necessarily the best when it comes to speed or efficiency, unless you're thinking of efficiency as actually saving money. So this is like Cox Internet 101, how to save money, basically. So, you know, when you want to split a node or something like that, it means, you know, create another connection so that not everything goes through here, you know. Maybe splitting the node is going to allow us to have another edge here, which will ease congestion, because now instead of everything going to 1, now they can split it between 1 and 7. You know, so, but anyways, that's besides the point. Okay, so that's basically what a minimum spanning tree is and how do you use it. I don't have anything else that I want to say about them. Notice that if we don't consider using the same edge to go back and forth, there are no cycles in this graph. So there's no way from 1 to come back to 1 unless I go back to the same edge I came from. That's part of why it's a minimum spanning tree, because otherwise if there was a cycle, that means there would be multiple paths to take. We're trying to go cheap as possible. If there's multiple paths, it means that we can remove one of them so that there's no longer multiple paths and there's just one path, you know? Another thing is with a minimum spanning tree is if you remove another edge, you will be guaranteed to lose connectivity to some part of the graph. Okay, so next let's talk about an actual implementation of an algorithm to solve this problem with a bigger picture. Because if you have, you know, we're looking at this, it's easy because we made an assumption when we were doing this, and that is, as we were working through this graph, I have a picture, I have it here again. You know, when I said like to remove like this edge, I asked you, is there still a way to go from 3 to 5? And I said like, yeah, sure, we can go this way, right? Okay, trivially we see that, but that's because it's a tiny graph. It's got what, like 9 vertices? What if it had a billion? At the beginning, it might be easy to remove edges, but as you get closer to the minimum spanning tree, you have to look to the entire graph to see whether or not you really have a connection. And that's a very, very expensive process if you're just doing it in a naive way. And so trying to do this in an efficient way turns out to be quite a complicated problem if you do it wrong because of that sort of check. So yes, this looks like an easy thing to do, and it is indeed easy for small graphs, but when you get to something serious, you have to do this algorithmically. Otherwise, you're going to make a mistake and not remove an edge, or you're just going to make it super inefficient to actually run through. And so Prim came up with an algorithm that is actually very similar to Dijkstra's shortest path, as you will see when we cover that next week. But for now, we're going to stick to just, of course, talking about Prim. And you will see that it's a very elegant algorithm and very, very clean to implement. And so the way that it works is we need to keep track of 4 things. And if you remember to breadth first search traversal and depth first search in the earlier videos, we had the idea of a visited array where once we visited a vertex, we mark it as done. And in the case of the breadth first search and depth first search, we use a stack or a queue, and when those were empty, we would say that we're done. In this case, we say we're done once we've marked everything as visited. Or vertex are just going to be identifiers. They don't have to be numbers or letters. They can be anything. You can just randomly assign them to be anything as you're sort of looking to the graph. So how do you look to the graph initially? Do a traversal, breadth first search, depth first search, just to generate all the possible vertices. And then you can go ahead and use that list to actually start doing this algorithm. The next thing that we're going to do is we have the concept of a key, and the key is going to represent the cheapest weight, so the lowest weight to get there from somewhere else. And initially we're going to start those out at infinity with the exception of the starting point. Now, in this algorithm, it doesn't matter where you start from, just like it technically doesn't matter in breadth first search. I mean, you will get different answers with breadth first search depending on where you start from, but I'm saying that in this, because a minimum spanning tree is a minimum spanning tree, you will get the same answer regardless of where you start. Now, if there's multiple minimum spanning trees, this algorithm is going to just give you one option, although I'll show you when you should detect that there's multiple answers. But suppose that you coded one way, it'll always give you that one answer. And of course, if you started it somewhere else, it might give you a different answer. So there's a variation there. The parent column row there is going to, every time that we update the key, we're going to want to save where that came from. And that's going to be useful when we're finished to actually draw the final minimum spanning tree. And so the algorithm is quite trivial actually for such a complicated problem. And this is it right here. And so what it says here is that for all vertices that are an element of the graph where the v to visited is not equal to true yet, so that means that while we're not done and having marked everything as visited, continue, and you're going to pick the smallest key that is remaining. So you're going to pick the smallest value of the key as the next vertex to start working with. And when you start the algorithm, you initialize that vertex you're working with a key value of 0, which of course is smaller than infinity, which is why when you start this algorithm, you will correctly pick that as the first vertex to work with. Now, once you pick that vertex to work with, you're going to loop through all the edges that are coming out of that vertex, and then you're going to work with those, okay? So for example, in this case with A, we're going to work with edges A to B and A to D, and those are the two that we're going to be working with. Okay, so for each of those edges, you're going to check the weight of them. So when I say the weight from U to V right here, I'm talking about checking the weight from that. So for example, for A, we have A to B and A to D. So I'm asking you what the weight from A to D and what the weight from A to B is. And that turns out that from A to D is actually 2, and from A to B is actually 2 as well. Okay? And so I can color code them so you don't get confused, but that one is talking about this one. And then this one, I can draw it nicer, A to D, is talking about this one. Okay, and so that's what the WA to D stands for. V dot key is just simply asking about these values here. So right now, if we're looking at V in this first example is going to be D. So we're saying is 2 less than D dot key, and the second we're saying is 2 less than B dot key, which of course in this first initial example they both are infinity, and the answer is yes, 2 is less than infinity. And so if that is true, and this is the important part, and this is actually the issue that I had originally in when I first live streamed these, and we corrected it in the live stream. You can check Twitch for that. But I still wanted to record it to avoid confusion. So you didn't have to like watch something wrong and then me correct myself. Might as well just give it to you correct the first time. So this is the part we missed. We forgot that in addition to checking whether the key is, whether the weight is smaller than the key that you have right now, you also don't want to compare this with any vertex that you've already marked as visited. In this case, the only one that we technically have marked as visited is going to be A, because that's the one that we're working with right now. But and you don't want to compare against yourself. But once we go further, we do not want to compare against, like when we look at another vertices, we don't want to compare back with A because it's already marked as visited. And if you do this, you'll run into some problems. So don't do it. And the problems you will see them when you try to draw the minimum spanning tree. So in this case, neither of those have been marked as visited. So D dot visited is equal to true. And the same thing for that one. Okay? My bad. I meant to say not equal to true. 3 classes in. This is getting tiring. Okay. So in that case, because that is true, we go into the if statement. And so we are going to update these keys with the new values that we found that are smaller. So the value is smaller than infinity for both D and B. So that means that B and D are going to be updated to be 2. In addition to that, we're going to update the parent of those, so D's parent and B's parent, with what we're updating them from, which is going to be our U. Our U is basically the one we're working with, so that's A. So that's saying, how did we get here? We got here from our source. By the way, sometimes you hear instead of parent the word source there, and so our source is going to be A. After we finish looking for all of the edges here, then we will have completed working on this, and I want to put this here so this is not part of the loop here. This is outside of the loop. So this goes like this. Like that. Okay, so it's not part of the loop. So once you finish doing this for all of the edges, you're comparing and you're updating them as necessary. Once that process is complete, now we can go ahead and actually update the visited to true if we haven't already done that. You could also do this at the beginning, so you could put this before the for loop if you prefer as well. But it doesn't really matter. Okay, so we marked it already as that. It's a Boolean array. Okay, cool. So we can go ahead and now move on to the next vertex. And to pick the next vertex, we're going to pick the one with the smallest key. In this case, we have three choices. We have B, C, and D. C is infinity. That's a big number. That's going to be not going to be the smallest one. Both B and D, however, are the smallest one. They're actually tied for the smallest one. That's the sign when you're doing this algorithm that there's more than one solution to your minimum spanning tree, at which point you can handle that accordingly if you're required to show all solutions to it. You basically can remember this and then take a different selection the next time that you run it, or if you're doing this recursively or dynamic programming or however you choose to do it. In this case, however, we are just going to go from left to right and arbitrarily pick one of them, in which case we're going to pick B. So we're working with B now. So for B has two edges coming out, B to C and B to D. So that's going to be the weight from V to C and the weight from V to D. Yep. And also actually B to A. Yeah, there's another edge coming out from B to A. And so these values are equal to, actually, to stop having to scroll around, let me go ahead and just move this down here. Make my life easier. There we go. So B to D is 1, or sorry, B to C is 3. B to D is 1, and B to A is 2. Is that smaller than what we currently have in C dot key, D dot key, and A dot key? Well, it turns out that C dot key is infinity, so that's definitely smaller than infinity, that's for sure. D dot key is going to be 2. That's true as well. And then A dot key is equal to 0. And technically, yeah, this is also this is false, but usually doesn't actually matter, because here's the thing: the second part of this is whether or not C dot visited is set to true, D dot visited is set to true, and A dot visited is set to true. In this case, A dot V is set to true already, so this is going to evaluate to false. And because this evaluates to false, we stop working on this one, so we don't even mess with it. I mean, I know this evaluated to false in the first place, but had it not, we stop. Otherwise, we will make a mistake. For the others, however, they do evaluate to true, that because they have not been visited yet. However, and both of them actually will get updated. So let's do that. So 3 came from B. However, we almost made a mistake here. But we didn't, because we're that good. This D gets updated to 1 because that's smaller than 2. And we're going to set the source to B or not to be. That is the question, right? And so this relaxation of that edge from 2 to 1 is basically me saying delete the edge from here because we don't need it. We have this edge from B to D that's 1 and it's smaller than B to D is equal to 2, okay? So I suppose this version is going to give us probably, if I was to predict, it's going to give us this graph. More than likely, this iteration of the algorithm is probably going to give us that graph instead of giving us the other one, which would have been this one. Okay, they're both minimum spanning trees. If we had picked D to work with instead of B, then it probably would have given us the other one. Not probably, 100%. Okay, so we can mark that as done now because we worked with all the edges. And so now we got C and D left. We're going to pick the smallest weight. That one we only have one choice, and that is to pick D. So we're going to start working with D, and D has 3 edges coming out. It has the weight of D to B, the weight of D to A, and the weight of D to C. Now, I know that I wrote it like this. If WUV is less than V key and visited is not equal to true, but ideally you want to flip that around and you want to put the V visited is not equal to true first, so you can take advantage of your programming language, which C++ does, has short circuit evaluation. Because if you use short circuit evaluation, you don't have to do that comparison, and that comparison is computationally expensive in the sense that it has to compare those two numbers and it has to dereference v.key as well. So you know, if v.visit is not equal to true, you don't even need to worry about that. It's never going to be the case, right? So you might as well check that first before that. So if you're coding this, you do want to flip that. You will see an improvement potentially if the compiler is not already doing this kind of thing for you. So and that's actually in reality how we would want to check it, because here, before I even go and consider these things, I know that I'm not going to do anything with this one, the top one, because D has already marked as done. A has already marked as done, so I don't even need to look at them and worry, because I know that whatever those weights are, even if it's less than that, then the visited part is going to tell me not to touch it. So, you know, for now, just to show you, I'll put them what they would have been, or they could have been. D to B would have been 1, D to A would have been 2, and then D to C is 5. So D to B, technically 1 is less than 2, so we would want to update this one. We would want to update this to 1 and put here AD. However, that is absolutely wrong, and that's the type that we had before. That's wrong in the sense that we don't want to do that because it's already marked as visited, so do not update that. If you do it, this thing will break. So you don't mess with it. And again, you don't even have to worry about doing this comparison if you look at that v.visited part first. With A, you know, we have a 0, 0 is less than 2. So in that one, either way, you would have gotten false from either part of that if statement. But, you know, there you have not much of an efficiency gain per se, unless the Boolean check is faster than the actual computation to compare. But the first one you did. Finally, for the last one, 5 is not less than 3. So that one you compare, false. That's right. You have to compare. You have to do both parts because first part evaluators are true, so you have to check that second part of the if statement, which then evaluates to false, and then you can say you're done. So in this case, we will go ahead and mark D as completed because that doesn't do anything. And finally, when we get C, what you will see here as a shortcut is that when you're at the last vertex, there should be nothing that gets updated because everything else has been. And so everything has been marked as used. So there's no way that anything can be updated. So like C to B and C to D, you know, that's a 3 and a 5. So even with the weights, they wouldn't have been updated. But even if they were for some reason smaller, they cannot be updated because everything has been marked as visited and you can't do anything. So at this point, nothing happens. So now you're done. You're actually complete doing your first ever minimum spanning tree algorithm, Cresco, or sorry, Prims. And so now how do you actually draw the graph from this? Okay, so one of the easy ways to do it is you can start out with the starting node that has no parent, so this one. And then from there, you are going to go to any of the next vertices that have those as a parent and draw it out. So start out with doing your A. And then from there, see what nodes have A as a child, or sorry, as a parent. And so you can see B has a parent. So we're gonna put B in here. And then you can see which nodes have B as their parent. And there's two of them. There is C and there is D. And so we can go ahead and put them. And in addition to that, we can go ahead and also put in the weights if you really want. So B and then BC. And then DB1. And I suppose that there it comes in the tree part of the minimum spanning tree name, because this looks more like a tree than a graph, but it is technically a graph, and it's not binary. You could have you could have a graph where it's just there's more than 2 out degrees, although because it's undirected, the out degree and the in degree are usually the same. So actually, B has 3 out degree and 3 in degree as well, just degree of 3. And so the first thing you're like, whoa, these things don't look the same. Yeah, but you gotta think 3-dimensionally or something. Like, you gotta think that they may not look the same, but you could fold this graph and manipulate it to come up with the same thing that we have up here. So like, for example, I'm gonna try to visually do that for you, because I'm not gonna do that for the other example. But you can see here that the way we have this, if we just grab this right here and we kind of bring it down and swing it around, you can see that the more you move this, you can eventually swing it down like that, right? So all I did was take this and bring it down over here. Okay, so I just swung that little branch down. It's still connected the same way. Okay, I can do the same thing with this one. If you can think of this 3D, I can like fold it over here like I'm folding a book. So imagine this is a book and I'm folding the page over here. I'm lifting it in my hand and bring it on this side. That's the same thing I'm doing with here. I'm lifting it and bringing it on the other side. And if I do that, I would bring it over here and I would end up with the same graph that I started with. Now you're asking, is this part of the algorithm? No, it's not, because again, it's a graph. You represent a graph within the GCC matrix or a GCC list or just pointers. But drawing the graph, there's an infinite amount of ways that you could potentially draw a graph. Just because like if you tweak it, you make a line curly or something, now it's a different graph potentially. So ultimately, they all represent the same graph. It's just drawing it differently. As you saw the different iterations of this. So if I did A, B, D, and then C like that, that's the same graph as this one. You have to be able to recognize that, which of course makes it amazingly fun to grade these things and test, because anybody could draw different graphs. So the TA has to actually kind of look at them and look, it's like, is it the same graph? Obviously these, it's easy to see the difference, but maybe with the first one that I had, you have to kind of stare at it for a minute if you don't know what you're looking for. Although most people seem to end up with the same types of graphs, just the way it works. But anyways, that's pretty much all there's to it. So let me take some water break here, and then we're going to do a bigger example, and then we're going to call it a day. A bit of stretch. Don't forget, by the way, that's right, there's that like and subscribe button. So I hope you click that. If not, then welcome back. All right, so now we got the graph that we originally were working with by hand. We're going to do with the algorithm. And yes, it's going to be quite a long example. But again, I want to make sure you get all possible scenarios covered in the example. So, and you will see that yes, as we had before, there are two solutions to this. And before, again, if you had picked D instead of B in that spot where we were tied, you would have had the second solution there. Okay? All right, so we start out by initializing our keys to infinity with the exception of the one that we're starting with. And then we set the parents all to null per se and the visited boolean array to set everything to false. And now we can go ahead and commence. We go in, the smallest key is 0, which is our starting point. That's good. And now we're going to look at all the weights that are coming out of 0. And, you know, before I even get started, I'm going to copy this down here so that I don't have to scroll back and forth as well. And I'm going to make it tiny, maybe too tiny for you to see, but it's mostly for me to see. Okay? Maybe a little bigger, otherwise I can't even see it myself. That way I don't have to keep scrolling back and forth. And I can also zoom in a little bit. You can see that on video. Great. Make sure you watch this in HD, by the way. I think YouTube is throttling things and putting them in SD because of the current ongoing situation. But you can still manually select HD and things that matter by actually just clicking it. You just have to do it on a per video basis versus it being a regular preset like it has been historically. Okay, so we're looking at 0. And I'm not going to do this whole weight thing for every single one of them because it's going to take forever. But I will do it for a couple in the beginning, just to make sure you get that syntax. And because I do want to see some kind of work like this on a test. And so here we got, we're starting with 0. So, you know, our U is 0 and our V are going to be 1 and 7. And so we're going to be analyzing whether one dot key is less than that value. And one dot visited is not equal to true. And we're going to do the same thing for the second one. In fact, my handwriting is getting messy, so I'm just going to copy paste. Yeah, okay, that's the 7s. So as you will very clearly already have figured out, the weight from 0 to 1 is actually equal to 4, and the one from 0 to 7 is equal to 8. And both of those numbers are indeed less than infinity, and both of those are indeed evaluating to true because neither of them have been visited. And so that basically says to go ahead and go into the if statement, and we're going to go ahead and update our keys with those values, meaning that we're going to take one dot key and we're going to update it with the weight from 0 to 1, which we know is basically saying one dot key is equal to 4. And the same thing for the 8. For the 7. So 7 dot key is equal to 0, 7 weight. And which basically means 7 dot key is equal to 8. And for both of these, the parent, so 1 dot parent is going to be equal to U, which in this case is 0 for both of these. All right, and by the way, if you're watching this video and you also saw the Twitch stream, I would like to know your feedback on the quality of the instruction, because on one hand, we have the interactivity. You can stop me, you can ask me questions and things like that. But on the other hand, here's a little bit more of a directed approach with less distractions and less pauses. And some people prefer that. Some people prefer the more interactive manner. I think I personally prefer the more interactive manner. But, you know, for future, not for this semester, but for future references, maybe pre-recording things is better, or maybe live streams are better. I think live streams are better, but some people only like pre-recordings better. I don't know. So I kind of would like to hear your feedback on that, if that's you who have seen both the Twitch version and the YouTube version. Don't forget to follow on Twitch. Okay, and so by the way, every time I do this is because like my mouth is getting super dry from just talking nonstop. So I apologize for those weird facial gestures. But okay, So in this case, we're going to just do what we just did. We're going to update the key to 4 and set the parent to 0, and update the key to 8 and set the parent to 0 for both 1 and 7. So 1 and 7. And we're going to set the parent to 0 for both of them. And we're going to update them to be 4 and 8. And we're going to mark this as visited because at that point we finished with all of the edges coming out. And I'll make a point of highlighting what we've already taken care of. Because you're only really seeing each edge once in a way. Especially if you flip that if statement. And you check the true part first. Okay, from there we are finished with the first iteration. Now we are going to go ahead and look again at our remaining vertices and pick the one that has not been visited yet, which in this case is pretty much everything except 0. And from there, we're going to pick the one that has the lowest key value, which happens to be in this case 1. There's no other choice but 1. Oh yeah, it accidentally hit delete on that. So that's going to be this one right here. So we're going to highlight it just to point out where I'm working at right now. Okay, so that's where I am working at. And so I'm going to have to be looking at this edge and this edge. And I don't need to see this edge anymore because I have already marked 0 as visited. Okay, but I will have to see 11 and 8. And so let me go ahead and take my picture and bring it even further down so I can still keep track of that. And so I am looking at the weight from 1 to 2 and the weight from 1 to 7. And technically the weight from 1 to 0, as I said, that's not going to be useful for us, but still I'm putting it here for at least this example. And 4. Okay, and so we are saying is what we have at 2, 7, and 0, all basically infinity except for, actually no, not all infinity, I lie. Just the first one's infinity because this is infinity, but both 7 and 0 are not infinity. We have something in 7 and we have 0 something. So we're actually saying it's 8 less than what we currently have, which in this one is infinity. In 7 we have currently an 8, and in 0 we currently have a 0. And are they visited? For 2, are they not visited? And that's true, it's not visited. For 7, it's not visited yet. However, this is false because it has been visited. And we don't want to mess with it. So because this is false, then that's out of the picture. We don't even touch that. We are, however, going to look at those. And so in this case, it happens to be that this one on the top here, or in the middle, sorry, this 11 is not less than 8. So in that case, no update's going to happen for that one. The first one, however, though, you know, that is indeed true. 8 is less than infinity. So that one we will definitely update. Okay, so that is 2, 8. So this is going to be 8, and we're going to set the parent to the one we're working with. Sometimes I like to keep track of what I'm working with by putting a check mark. I haven't been doing that, but it's a good way to do that. In coding, you need to have some sort of saving. Basically, you store U. What is U when you're working with? But by hand, it might be a useful thing to keep track of that. It's so much easier to keep track of things when you're trying to explain at the same time as well. But you know, that's the life I chose. So that's going to be 1 there. And that's it. We've taken care of all of the edges coming out of 1, which is basically, basically this is the only one that did anything. Okay, so we don't forget, mark 1 is complete. And so now we have 2 and 7 both have the value of 8. So we can pick either one of them as the next vertex to look at. And so this is the part where you know you have more than one answer to your tree, because if you didn't, you wouldn't have this choice. So again, I'm gonna just go ahead and pick the first one from left to right. But if you wanted to have all solutions to your minimum spanning tree, you could indeed go either direction and pick one or the other, and do the entire thing, and which potentially could bring into even more choices if that was the case. Not in ours, but in other ones there could be. An example for that is if the 9 up here, if this 9 was a 10, that would mean that removing the 10 from either 5 to 4 or 3 to 4, if they were both 10s, that would tell you that you wouldn't be able to remove both of them, because you would lose contact with 4. So one of your solutions would have one of those edges left, and the other one would have another of those edges left. So you'd end up with 2 solutions for minimum spanning trees, depending on which of those edges you picked, if they were the same weight. So that means you would have a total of 4 combinations potentially. You would have one where you have this, you have this edge and this edge. That's one solution. You could have another solution where you have this edge and this edge, and then this edge and this edge, and then this edge and this edge. And that's of course assuming if this value was not 9 but 10. But because it's 9, we have a choice. We know for sure we have to pick 10 off, because that's the most expensive one. It's only that we basically can go either direction when both edges are the same weight, and it gives us that choice, just like it is happening over here with the 8s. All right. And of course, if this was an 8 here, that would make way more choices too, like a lot. So it's not just a binary choice thing like here. So anyways, we're gonna work with 2. So with 2, we got a lot of edges that we gotta check around. We don't need to worry about looking at this edge here, because it's already marked as done. But we have 3 edges we gotta work with. We gotta do that one, and that one. And so it turns out that 3 and 5 are infinity, so they are going to get updated, and I'm not going to go ahead and show you that, because it's, I've already shown you enough examples of that. So I don't want to put you to sleep totally. So this just becomes 7, and then for 5 it becomes 4, and the source node is 2 for each of those. So that will take care of those edges. 8 is a little more interesting to look at, because 8 already, 8 is not interesting at this point either, because it has not been looked at either. So my bad. I was confusing because we have vertex names and vertex weights all using numbers, and get a little confusing. But this is going to become 2 and a source of 2, and that's it. So that's an easy one. We can now say that we have victoriously completed that vertex as well. So let me go ahead and mark it with a color. Okay, and so that takes care of that one. The next one we're going to pick at is the smallest number. Oh, and don't forget, make sure you mark it as visited in your Boolean array. This is far easier to remember when you're coding, because all you're coding is that, and the code remembers for you. But by hand, we're not machines. We can forget things, but we can also do things machines can never do, at least today. But I think maybe for a very, very long time. Okay, so now we have a couple of choices. We got some infinities, which of course we're not going to pick, but we have 7, 4, 8, and 2. Node 8 has a weight of 2, or a key of 2, which is the lowest one. So then that's pretty defined. Okay, we're going to go there. So let's go ahead and travel to that node. This is the color. Yeah, this is the color. Okay. So welcome to node 8. May you find your stay pleasant. Node 8 has a couple of edges. It has that one, and the one that we came from. 6, let's just do that one immediately, because that one is infinity right now. So we know the whole 9 yards here. It's going to say it's coming from 8, sorry, it has a weight of 6 and it's coming from 8. Node 7, on the other hand, that one, it's a little more interesting. So let's actually elaborate on that one. I'll do it right here and then I'll copy and paste it lower. So that is saying check the weight from 8 to 7, and that is equal to 7. And so now we gotta say, is this less than 7 dot key what are you doing? Dog is sitting here making some weird noises. Okay, so we're saying is W87 less than 7 dot key and is visited not equal to true. Okay, well, we said this is 7. So is 7 less than 7 key, which has 8? Yes. And has 7 been visited? It has not. So then therefore this is true. And so this means because this both are true, this part values are true, then we can actually go ahead and go in the if statement. And so now I'm going to copy this down to the bottom here. We can actually go and update these values accordingly. So in our case, though, V is 7 and U is 8. And so this is basically equal to 7. So we're basically updating 8 with 7. Okay, and we're setting a new parent. So that one is cool because that's what we consider relaxation of that edge. And that's the thing, more of a term for shortest path problems, but it applies here too, I think. And so in that case, we are going to go ahead and say that this node that originally has a weight of 8 is going to go ahead and do 7. And then from there, we are going to go ahead and change the source node or the parent node to where it came from, which was 8. So that's an important one. And what that's really telling us is this is not part of the minimum spanning tree. Because we have made that choice to keep the 8 on top, we're basically kind of throwing that one away. And so that's what's happening there in that relaxation step. So every time that you're replacing an edge, you're kind of throwing that old edge away and saying that's not part of the minimum spanning tree because I have found a better solution that uses less wire, less distance, a smaller sum of the weights. Okay, and so you don't need to look at the 8 to 2 edge because what are you doing? I'm gonna kick her out because I don't think she feels good. So, hey, Padme. She was feeling sick the other day, and I don't want her to throw up behind me while I'm trying to give a lecture. Okay. Sorry, Padme. Go have fun. Okay. So, yeah. Basically, if you go from 8 to 2, you can see that 2 has a value of 8, right? So if you were to say 8 to 2, which that is equal to 2, and you were trying to compare 2 is less than 8 dot 2 dot key, which is equal to 8. So you're saying 2 less than 8, which is true, so you're like getting all hype. But then you gotta say 2 dot visited is not equal to true. That is false because it has been visited. And so that is why you will not relax that step. If you do that, you will mess things up. That's the typo that we had the first time that we did this on Twitch. So, yes. Apologies for that. Forgot that. Okay. that point we're done. We mark everything and then we're done with 8. We can move on to the next lowest weight. In this case, the choice is clear. We have node 5, vertex 5, right here with a weight of 4 for the key. The other ones have either infinity or higher. Well, not higher than infinity, I'm saying higher than 4. So there's a 6, there's a 7, there's another 7, and then there's an infinity. So yeah, we're going with this one then. Okay, so let me go ahead and highlight it. So we're working with this guy over here, and from there, well, let's do the easy edges first. Again, you will do this sequentially, but I'm just doing it to kind of get done quicker here now. That's going to finally get updated from infinity, and it's going to become 10. And you can see later on it should get updated back to 9, but not yet. So that's cool. That's going to be a relaxation step in a way. That means that we found a path, but then we found a better one, so we're throwing the old one away. Okay, and then we can go ahead and do this edge over here. 5 to 3. Is 14 less than 7? No, it's not, so therefore we do not update 3. Over here, however, that one is probably going to be doing some updating because we are looking at the weight from 5 to 6, which is equal to 2. And we're saying is 2 less than 6.key. 6.key currently has 8. So 2 is definitely less than 8. And 6 has not been marked as visited. So therefore we are ready to make that relaxation there. We're going to go ahead and change that 6 to be a 2. And we're going to make the source a 5. And you know, that's a big one right there. We just saved a lot of space by doing that. And not space, but cabling, right? Because before it was a pretty big number there. What happened to that? That was probably an 8 there, or what was the number there? We lost the number. That was a 1. Fortunately, that we won't mess things up because we haven't fiddled with it yet. So I think we'll be okay. But yeah. So anyways, 6 got updated to 2, and that is good to go. So let me go ahead and paste that here. And don't forget to mark 5 as complete. Okay, so we got 7, 10, and 7. Oh, we have a 2 here. I was like, ambiguity. There must be more than one minimum spanning tree, or more than 2, but I don't remember that, so I kind of worried. But then I saw that we have a 2 here, so that's definitely one I pick as the choice. And so we shall pick that indeed. So that's a yellow right here. And so that is, from that one, because both 8 and 5 have been marked as visited, we don't have to worry about that. The only edge that we really have to look at before we can call it a day on this vertex is this edge right here. And it's an important edge because it's a pretty small edge. So more than likely that guy is going to relax something, And so we can go ahead and take a look at that and see. So that is the weight from 6 to 7, which is equal to 1. And is that less than what we currently have in 7.key? And it has 7 been visited? It has not been visited yet, so we're good in that regards. And 7.key is actually 7, so 1 is definitely less than 7. So this is 1 that's definitely going to get relaxed. We just saved their 6 kilometers of cabling. Cox would be totally all over that one. And so the new source of that is going to be, of course, the one we're working with, which is 6. And we can then go ahead and say we are done. We're going to get higher for wire placement now, because look at how much wire we're saving from this network. Who cares about the slow internet the customers get, right? Imagine caring about customers in 2020. Sold. All right, next we are going to be looking at 7, because it has a key of 1. As you can see, these key values change all over the place. So not just like before, 7 had a bigger value, and the next thing to check could have been something else. But now it's the smallest one. So you got to recheck that every time to make sure that you're picking the next smallest one. And that is like a dynamic thing that's changing around. So you can't just commit to one choice ahead of time to try to be more efficient and like parallelize this or something. In this case, though, there's no edges to look at because edge 0 and 1 are already visited, and 8 and 6 are visited, so there's nothing to do there, so nothing happens. That's pretty much the end of that. Then you get to 3. When you get to 3, you're gonna really only be looking at one edge, and that's this edge, which should relax this one down here, as we were giving you that example earlier. So the way from 3 to 4 is equal to 9, which should be less than what we currently have, which is 10, which is what 4.key has. And so that is true, and it hasn't been visited yet, so we can go ahead and relax that. So that is basically taking over that edge. It's saying, nah, this is not a good edge. This is a better edge. He's a better player. And so that is saying 9 and change the source. No longer it's going from 5 to 4, but now it's going from 3 to 4. So there you go. And I think that should be the last edge that changes. We can go definitely and mark 4 as complete. Or we were working with 3, my bad. Yeah. So we can mark 3 as complete. And so with the last one, so we just did this one. Technically we'd have to look at 4. But when you only have one vertex that's not visited yet, it's impossible for it to change anything else. So you can actually stop here in the algorithm and save some time complexity. But if you don't, you would look at it. You look at 4, see 2 edges, see that both are already. It doesn't matter whether you can update it or not because they're already visited. So you would just be like, you're done. And now, hopefully, we have the right thing. And so I'm going to go ahead and copy my chart down. We're going to try to draw the graph. Dog's getting triggered because I kicked her out from being near me, I guess. She went downstairs. Sorry about that. Okay. And so, all right. Hopefully we get that same graph. Moment of truth, guys and gals. Okay. So we can start out with the parent that has nothing in it. So it's C. 0, not C. From there, how many vertices have that as a parent? Just 1. 1. How many vertices have 1 as their parent? And just one of them, which is 2. How many vertices have 2 as their parent? Well, we got 2 of them actually. We got 1 over here and we got over here. All right. And you could put them in any direction you want, but I'm kind of low-key cheating and trying to make it look similar to this so that we can get something similar. So we know we got 3 and 8. So we could put 3 here and we could put 8 there. But, if we wanted to look kind of like what we had originally so that you can I can prove to you that it's actually the same graph, I'm going to go ahead and kind of put 3 here and 8 here just to get the same thing. Okay? And as you do this, you should be including the weights. You could also do it at the end, but you should. Like, this would be a weight of 4 here. This would be a weight of 8. 2 to 3 would be a weight of 7. And 2 to 8 would be a weight of 2. And then you could even circle them if you want. But actually, I'll add the weights later because I want to add them in a different color. So anyways. Okay. So that takes care of 2. Let's look at 3. Is there any edges coming out of 3? Yeah, there's 9. Okay, and by the way, how can you do this algorithmically, like build a graph? You could do this recursively, like in a depth first search way, and then you can keep a stack so that you can come back and build more. Or you could do this backwards as well. You just to kind of Lego it backwards, but I think the easiest way is with the stack. So if you want me to show you that, I can actually. So yeah, why not? After all, you do have to code this, so I'll show you the actual algorithmic way to do this part. So again, you start from 0. Now you need to have a stack data structure. Okay, and we're going to push things in the stack that we don't get to in the order that we. Breadth first search should work as well, by the way, but stack just seems to me the easiest one to think about. So again, we start with 0, and then 0 we have one thing, so we can just jump right in. And then from 1 we have 2, which again is just one thing. And then we have 2 things, right? So what we'll do is we'll pick 1 to add it, and then we'll add the other one back into the stack. So we can add 8 to the stack. Okay, and then we can go in the route of 3 first. Okay, once we're at 3, we can, and by the way, if you want to make your life easy, don't just add the 8, add where the 8 is supposed to go with into that, and just dump it in there. Okay. And then, and if you don't need a stack, by the way, if you do this recursively, but if you're doing it early, you would. Okay, so from 3, you are going to go to 4, and I think I gotta draw this way now, so it looks like the final result. And 4 has nothing else to come from, at which point you can pop whatever from a stack and go from there. So you can pop this out and you're back at 2, and you can do 8 now. 8 has nothing on the stack, at which point you probably screwed up somewhere. Why didn't we have anything coming from here? We have 1, 2, we have 3. Oh, the 5. See, the 5 was also coming in from there. We never added that in. There was 3. So technically, we had the 2 here and the 8, and we also would have had a 2 and a 5 in the stack, because that's also coming from 2, right? So we go ahead and we popped out the 2 and the 8, and then we have nothing else to do with the 8, so we can pop out the 2 to the 5, and we can do that one. So 2 to 5, here we go. 5 takes us to 6. 6 takes us to 7. And 7 doesn't take us anywhere else. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. Did we get about the same thing? 0, 1, 2, 3, 4, 7, 6, 5, 8. Yep. And if we were to copy the weights down as we had done this, which like I said I wanted to do but in a different color, this would tell us 0 to 1 is a 4, 1 to 2 is an 8, 2 to 3 is a 7, 3 to 4 is a 9, 2 to 8 is a 2, 2 to 5 is a 4, 5 to 6 is a 2, and 6 to 1 is a 7. And how I'm looking at it is, like, for example, I'm looking at this number and then this number, and then I'm getting the weight. That's kind of what I'm doing. Okay, and so that is indeed, I think, the minimum spanning tree that we had up here. So let's go ahead and pull it out. This version, right? Because remember, there's 2 of them. And yeah, I mean, it doesn't look as pretty, but it definitely looks right. So we did it. We got it. And another way they can check is we can check the weight of this and see if it's the minimum weight compared to the previous one, which we had 37, I think. And if you were to add it up, you would get the same number. So there you have it. There you have a correct, nice and clean example of a minimum spanning tree that's pretty considerate. And like I said, the time complexity of this algorithm is v squared, v being your vertices. It can be e log v, edges log v, if you do it with a binary heap. But that's something you probably talk about in analysis of algorithms, if even. So, there's no one here to ask questions, so I hope you all got it. And if not, then check the Twitch. There were some questions asked there. You will have to implement one of these for your assignments. So I do hope that you understood this one, and if not, maybe you'll get the other one better, but you still need to know both for the test. So with that said, we are at 1 hour and 24 minutes, so that's pretty long. That's pretty much a full class. So there you go. I hope that you enjoy this recording. And again, sorry that I made the typo in class, but at least I re-recorded. I made up for it because I felt bad about that, to be honest. So, all right then. Thank you all for watching. As always, I hope you guys have a wonderful day. Take care, stay safe, and see you next time.